Today's lesson is 1.3.2, creating and graphing exponential equations. And our objective is that students will be able to graph exponential equations. So you'll notice that we're starting off with a word problem today. We are going to use that word problem to create an equation just like we did the last lesson. And then once we create that equation, we are going to actually graph that equation. So if you haven't read the problem yet, read it along with me now. It says, if a pendulum loses 10% of its height on each swing, and it starts with a height of 60 centimeters, what is the equation that would represent this scenario? So, let's start out with the equation. I noticed that it says it's losing height, so I'm going to use the exponential decay formula. So my formula, or my equation, is y equals 60 times 0.9 to the power of x. I found that by substituting my height of 60 centimeters, my percentage lost, which was 10%, or 0.10, and then combining 1 minus 0.10 to get 0.9. So first thing that I need to do is create a table of values by choosing x values. So I've created my table, and I'm going to go ahead and choose the x values I want to use. There are no set values that you have to use. Really, you want to look at the equation, kind of ask yourself which ones make sense. So 0 is always a good one to use because anything to the power of 0 will equal 1. 1 is also a good one to use. And then from there, you can just kind of decide. For this one, I'm going to do 2, 3, and 5. Next thing I need to do is substitute my x values and solve for y so we can complete this table. So let's first substitute 0 in place of x. Y equals 60 times 0.9 to the power of 0. Well, I know anything to the power of 0 equals 1, so that's going to turn into 60 times 1. And 60 times 1 is just 60. So that means that if x is 0, y has to be 60. So we'll put a 60 in there. Let's go through and do the same thing for our other x values, which are 1, 2, 3, and 5. So I have 60 times 0.9 to the power of 1. 60 times 0.9 to the power of 2, 60 times 0.9 to the power of 3, and 60 times 0.9 to the power of 4. So go through and simplify each of those little equations that we now have. Remember, we need to do exponents before we do multiplying. So take a minute to calculate each of those. So I came up with when x equals 0, y equals 60. When x equals 1, y equals 54. When x equals 2, y equals 48.6. When x equals 3, y equals 43.74. And finally, when x equals 5, y equals 35.43. Now let's move on to step 3, which is to assign labels to your x-axis and y-axis. So when we're assigning labels, x is usually going to be time, y is usually going to be the total. So in this specific problem, we are talking about a pendulum swinging. So we don't have like minutes or hours in this problem, but we are measuring time based on the number of swings. So each swing is going to represent the x value, and we're trying to figure out the height of the pendulum. So the height is going to represent our y value. So let's move on to a graph page, and I need to label my x-axis as the number of swings, and I need to label my y-axis as the height of the pendulum. Sometimes the labels are going to be really obvious to you. At other times, you might have to really think about what you want to label each axis as. Okay, let's go back and take a look at step number. So step 4 is to determine the scales. Your y-axis is typically going to have a large scale because we are either adding or subtracting your y values very rapidly. That's the nature of exponential growth and exponential decay. So in this case, where I'm starting up at 60 and it's getting smaller and smaller every time, I want my graph to go all the way up to 60. So I counted by 5s, and I only numbered the 10s. So we went up 5, 10, 15, 20, 25, 30, all the way up to 60. On my x-axis, I went by 1s because for every time I go down 10%, I have one single swing. All right, now we have this nice table of points right here. And we're going to take these points and we're going to plot all of them. So we have the point 0, 60. So I'll go right over here to 0 and we're going to plot our first point there. 0, 60. And if you take a look at our table, the next one is at 154. So I'm going to go over to 1 and then almost all the way up to 55. We're going to start just below that at 54. Now go through and I want you to plot all of your points on your graph. So I have my 5 points on there. You'll notice that these points aren't evenly spaced out. They're spreading further apart as we go down. So when I connect these points, it's not going to be a straight line like it was before. Now it has a nice curve to it, and that curve is just going to keep going and going until it gets closer and closer to 0. One thing that is special about this is that you cannot pass y equals 0. So my curve here is never going to pass the x-axis. It's just going to get as close as it can to the x-axis without actually touching it. Let's look at one more example together. So our next example is the bacteria, Streptococcus lactis, I'm sure I said that wrong, doubles every 26 minutes in milk. If a container of milk contains 4 bacteria, write an equation that models this scenario and then graph it. So let's start out with our formula. I noticed that it says it doubles. Doubles is kind of a hint. And that it doubles every 26 minutes. That's that 4th formula that we use when we have something that's changing not at a rate of 1. So my starting value is 4. The rate is to double. I don't know what x is, but I know whatever it is, it happens every 26 minutes. So now I've got to go and I need to create my table. So here's my table with x and y. I'm going to start with choosing 0 because it's the easiest thing to substitute into an exponent. Now rather than going to 1, I want to think about this for a second. If I were to substitute a 1 in place of x, then I would have 1 over 26, and that's kind of a nasty fraction. So I want to substitute things that can be divided by 26. So if I substitute 26, then when we substitute 26 into x, we'll get 26 divided by 26 is 1. So I'm going to do 26, 52, 78, and 104, because all of those can be divided by 2. So for the first one, our 0. 0 divided by 26 is just 0, so that's going to stay as 4 times 2 to the power of 0. Anything to the power of 0 is just 1. So for our y value, we get 4. Now when y is 26, 26 divided by 26 will give us a 1. 4 times 2 to the power of 1 is the same as 4 times 2. And 4 times 2 gives me 8. Now let's substitute our 52. Well, we need to simplify our fraction. 52 divided by 26 is the same thing as 2. Now it's time for the exponents. 2 times 2 is 4. And 4 times 4 is 16. So you'll see if I would have chosen something like 4 to put in place of this x value, I would have 4 over 26, which reduces to 2 over 13. And that just makes things way too difficult. So choose things that will give you a nice exponent. If you finish substituting these values, we'll find out that when x is 78, y is 32. And when x is 104, y is 74. So I've created my equation, I have my table, I filled out all the y values. Now it's time to go on and label my x and y axis. So for this one, we have time going on where the bacteria doubles every 26 minutes. So I'm going to label my x-axis as time in minutes. And what's happening as time goes on? Well, what's happening is that our bacteria is growing. So my y is the number, that doesn't really look like a number symbol, the number of bacteria. Next thing I need to do is decide my scale. Well, to figure out the scale, let's look at the table again. So we go from 0 to 26 to 52 to 78 to 104. So I think I'm going to do my x-axis by going up 26 every time. My y starts down at 4 and it goes all the way up to 64. So I actually want to go up by 4s. So I changed my mind and actually went up by 8s because I didn't have enough room to go up by 4s. So my first point belongs at 0, 4. I found by looking at my table right here. First point, 0, 4. Second point will be at 26, 8. So let's go to 0, 4 and plot our first point. Next, I'll go to 26, 8. Plot my second point. Third point is at 52, 16. And then we go to 78, 32. And then finally to 104 and all the way up to 64. And when we draw our curve, we'll see it's not a straight line, but it's a nice curve that's increasing at an increasing rate. So it's going up faster and faster and faster. All right, don't forget the quiz for this lesson. And if you need to rewatch any of these, please rewind so that you will feel prepared for when we go over it in class tomorrow.